Hi guys, Michael here. So in my last video, I talked about how, as part of my participation in the Base 11 Space Challenge, I am leading the development of a liquid fuel rocket engine. So this week, I wanted to talk about exactly what that means. What is a liquid fueled rocket engine? How do they work? And what do you have to consider when designing them? So most of the content of this video is sort of a distilled version of the explanation I gave to my team when the competition started. So for starters, what is a rocket engine? What differentiates it from, say, a jet engine? The biggest factor in the difference between a rocket and a jet engine or any other type of engine is the fact that a rocket engine stores all of its fuel. In that, I mean it stores its fuel and its oxidizer. Jet engines, car engines, any other type of engine has some sort of air intake or some sort of fuel intake. A jet engine has an air intake, whereas a rocket engine stores that oxidizer separate from its fuel and has to mix it in its combustion chamber. Now that goes for all types of rocket engines, but there's two main types of rocket engines being solid or liquid, with a third being a hybrid, in that it's literally a mix of the two. Solid fuel rockets are fairly simple. They actually don't really qualify as a rocket engine. They are more of a rocket motor in that they don't have any moving parts. A solid rocket motor has its fuel and oxidizer mixed together into a fuel grain, which is then just lit on fire and burns until it runs out. There is no turning it off. It is very inefficient, but it is very simple, and it is a very simple way to provide a lot of power. On the opposite side of things is the liquid engine, where it has a lot of moving parts to move a liquid fuel and a liquid oxidizer from two separate tanks, mix them together, and burn them, and not blow up in the process. That is a lot more efficient in how it does that, in that it takes a lot more, it takes less fuel to produce more thrust, but they are very expensive in that there is a lot of engineering required, a lot of moving parts. Another benefit to liquid engines is that you can throttle them. You can't throttle a solid rocket motor. Well, you can, but you can't throttle on command. When you're throttling a solid rocket motor, that's designed into it. It's designed to throttle down at a specific point in time. You can't just flip a switch and tell it to throttle down. You can do that with a liquid engine. Last but not least is the mix of the two, the hybrid rocket motor, where you take a solid fuel grain and feed it with a liquid oxidizer. This has the simplicity, or most of the simplicity, of a solid rocket motor, as you have less moving parts, but you have the benefits of a liquid motor where you can throttle it. And the last big difference between a solid and a liquid or hybrid is you can turn it off if you want to. Solids just go until they run out of fuel. Liquid and hybrid engines can be shut off at the flip of a switch, which is a very big thing for safety. As the competition I am in specifies, we have to use a liquid engine. That is what we are focusing on, and that is what I will be talking about in this video. So, how does a liquid engine work? What makes it tick? What do you have to consider when you are designing it? The first thing is you have to consider how a rocket engine in general works on principle. It takes its propellants, its fuel and oxidizer, it mixes them together in some way, either beforehand or when the engine is firing. It takes those propellants, burns them, and then expels those exhaust gases to produce thrust. Everything about a rocket engine is about thrust, so that's a good place to start. What is the thrust? How do you calculate that? Most things about a rocket engine are based around the engine's thrust, so that is a very good place to start. The convenient thing about not having an air intake or any sort of intake on the engine actually simplifies the thrust equation. The thrust equation is simply your mass flow rate multiplied by your exhaust velocity plus the pressure differential multiplied by the exit area. Now, most rocket engines, to get the most efficiency out of them, equalize that pressure differential at the exhaust, so that whole term drops away. So we can just focus on thrust equals mass flow rate times velocity. As with anything in engineering, we want to make it as efficient as possible. And in this case, that means we want to produce the most amount of thrust for the least amount of fuel. As we can see with the thrust equation, we can get the same amount of thrust for less fuel by increasing that exhaust velocity. And that's the whole concept for how a rocket engine is shaped, is getting those exhaust gases to move as quickly as possible when they leave. These exhaust gases are sped up using what is known as a converging diverging nozzle. As with any normal nozzle, such as a garden hose, you can get your exhaust gases moving faster by reducing the size of the nozzle, by constricting the flow. And that works to a certain point. That is the converging section of the nozzle. However, gases are weird, and once they hit Mach 1, the convergence of the nozzle actually prevents mass flow rate instead of speeding it up. So once the gas hits Mach 1, we have to start diverging again, because the converging section increases the gas pressure, and once it hits Mach 1, diverging and reducing the exhaust pressure increases your exhaust velocity. The more you expand the gas, the lower the exhaust pressure, the higher the exhaust velocity. Now, this can only go so far, because once your exhaust pressure drops below your ambient pressure, you start to get problems. This is why most engines have an exhaust velocity or an exhaust pressure that is equal to your ambient pressure. That is why that pressure differential in that thrust equation usually cancels out. Now, the combustion pressure or chamber pressure of the rocket engine also affects your efficiency, because if you have a higher chamber pressure, you can expand that gas a lot more before reaching your ambient pressure. So higher chamber pressures correlate to higher exhaust velocities and higher engine efficiencies. The same goes for combustion temperature. A higher combustion temperature will equal a higher exhaust velocity. You can understand it better by looking at the math, but to simplify things, you can just see that more energy in terms of thermal energy or heat can be converted to more kinetic energy through the geometry. So because higher chamber temperature means higher exhaust velocity, rocket engines run with exhaust gases that are really, really hot. Now the problem that comes from this is these gases are usually hotter than the melting temperature of the engine. So we have to find a way to keep that engine cool and prevent it from melting. One way to do it is film cooling, which runs some of the fuel along the engine to insulate it, to prevent that hot exhaust gas from heating up the engine itself too high. Another method is ablative cooling, which is just having a insulatory material that burns away. The problem with both of these methods is they actually really hurt your engine's efficiency in a lot of ways. The most popular form of engine cooling is regenerative cooling. And this works by running your fuel through your engine bell and then into your combustion chamber to burn it. This works really well if you're using a cryogenic fuel, where your fuel is really, really cold, as in significantly below freezing cold. But even if your fuel is at room temperature, it's still a lot colder than the hellish environment of your exhaust gases. The great thing about regenerative cooling is not only do you cool down your engine, but you also heat up your fuel. And heating up your fuel means you actually get a higher chamber temperature, which translates to higher efficiency. The fun part about regenerative cooling is the fact that because heating up your fuel creates a higher chamber temperature, a higher chamber temperature means your fuel warms up more, which means a higher chamber temperature means your fuel warms up more, which means a higher chamber temperature, which means your fuel warms up even more, which means it's a closed cycle. It influences itself. So doing that math can be really problematic. Now this regenerative cooling can also be used to drive the engine, because your fuel, as it heats up, will also expand. And in the case of what's known as an expander cycle, you can use that expanded gas to drive a turbine, which then drives your fuel pumps. Now, a really big topic of discussion in engine design is what's known as the engine's cycle. This is how the engine drives its fuel pumps, and there's a lot of different ways to do it. I already talked about the expander cycle, but there's actually two forms of the expander cycle, but which are referred to as either a open or closed expander cycle. Open and closed cycles refer to what happens to the gas that drives the turbine. In an open cycle, the gas passes through the turbine and then is dumped overboard, either through a nozzle, which can be used for steering, such as on the Merlin engines, or it can be dumped around the main converging diverging nozzle, which can be used for cooling. A closed cycle, however, dumps this exhaust gas back into the combustion chamber, which can provide an increase in efficiency, but can also be far more complex, and if done incorrectly, can very easily tear the engine apart. So, in the early days of the space program, NASA used all open cycle engines because they couldn't figure out how to get a closed cycle engine to work. One of the most common forms of a open cycle engine is a gas generator cycle. And in this cycle, a little bit of fuel and oxidizer is actually run into a separate combustion chamber where that gas directly drives the turbine and is dumped overboard. This gas generator cycle is used by some of the most popular engines in the world, such as the F1 engine on the Saturn V and the modern-day Merlin engines used by SpaceX. Now, opposite open cycle and gas generator cycle engines are what are known as closed cycle staged combustion engines. Like a gas generator cycle, the turbine that drives the fuel pumps is driven by exhaust gas from a separate combustion chamber. But this is no longer known as a gas generator, but is now known as a preburner. Because instead of flowing some of your fuel and oxidizer through this smaller combustion chamber, you are now flowing all of your fuel and some of your oxidizer through this combustion chamber. This means your exhaust is mostly fuel, and with a little bit of combustion product. And that drives your turbine before going into your main combustion chamber as your fuel source. This is known as a preburner because your fuel is pre-burned before entering your main combustion chamber. It's also known as staged combustion because this combustion occurs in stages. First the preburner and then the main combustion chamber. This engine cycle is used by things like the RS-25 or the Space Shuttle main engine, and is really good for high efficiency, but is also incredibly complex. We can take this concept of staged combustion a step further, and a step towards the even more complex, by looking at what's known as full flow staged combustion. In this case, you have two separate preburners. One takes most of your fuel and a little bit of oxidizer, and the other takes most of your oxidizer and a little bit of fuel. These both do the same things. They both drive a turbine, which then drives its respective pump. The fuel-rich preburner drives the fuel pump. The oxygen-rich preburner drives the oxygen pump. And both of these preburners have either a fuel-rich or oxygen-rich exhaust, which act as your fuel and oxidizer supply. And they both feed into your main combustion chamber as your propellant source. In this cycle, none of the fuel or oxidizer goes directly to the main combustion chamber. Instead, they go directly to the preburners, where they then go to your combustion chamber. The reason for this name, full flow staged combustion, is fairly obvious, because all of your propellant is flowing through your staged combustion cycles. And this is an incredibly complex type of engine design, but it's incredibly efficient. It's what is going to be used on SpaceX's Raptor engine, which could be one of the most complex engines ever created, because not only is it running full flow staged combustion, but it's also running at the highest chamber pressure ever designed, 300 bar, and it's also designed to be reused. It's probably one of the most complex modern day engines. The last two engine feed cycles that I will talk about are actually the simplest. The first is what is known as a electric feed system, where instead of using a turbine to drive your pumps, you simply use electric motors. Electric feed cycles are fairly recent in use because of the recent advancements in battery density and electric motor efficiency. Back in the old days, the technology simply was not efficient enough to be used on a rocket engine. A turbine was a much more efficient way to do it, despite the increased engineering complexity. The last way to drive an engine is by far the simplest, and it is known as a pressure-fed system. This drives the fuel by simply having a very large pressure differential between the fuel tank and the engine. This doesn't require any pumps or turbines or electric motors. It simply works by driving the fuel and oxidizer via pressure. The reason why we don't see pressure fed on large-scale rockets is simply because of the pressure required. Rockets already use pressurized tanks, but not to this high of a pressure. We are talking pressures that if the tank were to rupture, the resulting explosion would be catastrophic. A lot of engine design is focused around the engine's efficiency. What is the best way to drive the fuel, the most efficient way to drive the fuel, the lightest way to build the engine, the way to get the most exhaust velocity, to use the least amount of fuel for the most amount of thrust. It's all about efficiency. The problem is rocket engines are really inefficient compared to other things. We only use them because for space applications, they're really the only way to do things. This is why there is a lot of work into how to improve engine efficiency, and it's all about getting that higher exhaust velocity. The problem is we are kind of up against the laws of physics on this end. Really, the only way to increase your efficiency up with conventional chemical rocket engines is to increase your chamber temperature or your chamber pressure. One way to do this is using more energetic fuels, but you still run up against problems, because as you increase your chamber pressure, you have to make your engine heavier to withstand those pressures without exploding, and with high chamber temperatures, you have to find a way to cool that engine to a point where you don't melt it. So most of the developments in engine technology is really material development. How do you design a material that can take these high pressures without failing, or take these really high temperatures without melting, or both? That is the heart of engine development. It is material development. So that is really the basics of rocket engine design. And yes, even the basics get fairly complex. So with that, I want to thank you for watching this video. If you have any questions, because I skimmed over a lot, if you have any questions, drop those in the comments down below. I will be happy to answer them for you. If you want to keep seeing videos like this, feel free to subscribe to this channel. Hit the like button if you enjoyed watching this video. I would like to know what you guys think of these videos. And as a reminder, my videos come out Thursdays at 7 p.m. So keep an eye out for those, and I will see you guys next time.